Taylor series are everywhere around us, be it in computers, phones, or even calculators. But why are they so important? Well, Taylor series allow us to simplify and approximate difficult functions like sine, cosine, or exponential effects into easier polynomials, meaning that a computer that can only do additions, subtractions, divisions, and multiplications can easily solve them. But how does it work? Well, let's go back to the beginning.
In mathematics, we know a function which the derivative is itself, the exponential function. We deduce this expression. What is annoying is that we can't easily calculate the number e, that is around 2.7. But knowing the relationship between ax and its derivative, could we calculate the number e? And the same problem with the cos, sine, tan, and many other functions. The expression of the derivative is also easy to write. Let's go back to the original problem, finding the expression of ex. We know that the polynomial function can represent any function with an infinite number of terms. We know that ex doesn't change when derivated. So let's derivate our polynomial function. What is interesting though is that the coefficient change when we derivate. But we are trying to find the coefficients a0, 1, 2, 3, and 4 in a way that makes their derivatives the same. Let's highlight the coefficients. To keep the same derivatives, we can replace a1, 2, 3, and 4 by the inverse of their coefficients. So here are our new coefficients. We can now build our final polynomial. To summarize, we found the coefficients a0, 1, 2, 3, and 4 in a way that makes their derivatives and time the first coefficient that stays 1. We can now compare ex with the polynomial. As you see, when increasing the number of terms, the polynomial becomes more and more accurate. And with an infinite number of terms, the polynomial tends to become infinitely accurate. But it worked for ax, but can we improve it to work all the time for any function? What we saw is that the successive derivatives must keep for first term 1. It worked because the derivative of ex at a degree n is always 1. It's important because our polynomial must have the same derivatives in the row to follow the same curve. We can now write the general formula to approximate any function with a degree 4 polynomial. But it's just an approximation, so we need to add the error for this degree. We can now write the general formula with an infinite number of terms as a sum. This is called the Taylor series. It's a way of approximating a function with an infinite number of terms in a polynomial. We saw a moment ago that there isn't an exact formula for the cosinus function. Let's try to approximate it with a polynomial using the Taylor series. First, we need to calculate the derivatives of cos x at x0. Now we can plug these values into the Taylor series formula. Let's substitute the derivatives we calculated. Simplifying the expression, we get this. Let's visualize this approximation. As you can see, the more terms we add to the Taylor series, the better the polynomial approximates the cosinus function.
Taylor series have many real-life use cases. As we said earlier, it is used in computers to simplify difficult functions. It is also used in physics to approximate differential equations and to calculate some analytical formulas. Finally, Taylor series can be used in finance to calculate bond pricing and determine risk. Thanks for watching.